This video we should be able to wrap up 3-5 rational functions and their graphs. We'll start here with example 7, just another rational function to graph using the 7-step process we were using before. Step 1, can we identify any symmetry? I see even exponents, all even exponents, and a plus or minus a constant doesn't hurt anything. So here we do have even function or y-axis symmetry. Number 2, y-intercepts. Plug a 0 in for x. F of 0 gives us 0 over 1 or 0. And that's a dead giveaway too for our x-intercept. If I set just the numerator, x to the 4th equal to 0, I also get x equals 0. So the x and y-intercepts both occur at the origin. Make the graph just a little bigger. So we're going to go through the origin. Number 4, vertical asymptotes. Denominator. Where does my denominator equal 0? Well, it's a squared quantity plus more plus 1, so it's never going to equal 0. There are no vertical asymptotes. How about horizontal asymptotes? I see my numerator is more powerful, x to the 4th, so that means this will increase or decrease without bound. There are no horizontal asymptotes. So let's just plot a couple points to the left and the right of our x-intercept and see what's going on. So if I plug in a 1, I'll get 1 over 1 plus 1, or a half. If I plug in a 2, I'll get 2 to the 4th. That's a 16 over 5, or about 3 and a 5th. So I'm up to about here and here. Oops, I went a little far over for that one. There we go. It's just the shape of a parabola, opening up. You can kind of get an idea. This is sort of like a little cheat, a little trick. If I look at just the leading stuff, x to the 4th divided by x squared, use their properties of exponents. We would subtract 4 divided by 2 is 2. So x to the 4th over x squared, its general shape is going to be like that of an x squared, or a upward opening parabola. Okay, we've done vertical asymptotes. We've done horizontal asymptotes. There's one other type. If it's not straight up and down, and it's not perfectly horizontal, it has to be at some slant. And that's our last type of asymptote. Examine the graph of x squared plus 1 divided by x minus 1. And it's shown here in the figure. Make it a little bigger. There we go. Note that the degree of the numerator is a 2, and it's greater than the degree of the denominator 1. Thus, the graph of this function has no horizontal asymptote. However, the graph does have a slanted asymptote of x plus 1. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. The equation of the slant asymptote can be found by division. For example, to find the slant asymptote of this, we divide x minus 1 into the numerator x squared plus 1. We can use a little synthetic division. Don't forget a 0x to the 1st for the missing power of x. Synthetically divide, and we get 1, 1, 2. The remainder's 2. So we can look at that as 1 x to the 1st plus 1 plus the remainder over x minus 1. Observe that, x squared plus 1 over x minus 1 is equal to this, x plus 1, which is a line, plus this remainder. What's that? The equation of our slant asymptote is this line, x plus 1. So as the absolute value of x heads toward infinity, this remainder, 2 over x minus 1, is going to become 2 divided by infinity, or it's going to approach 0. Thus, when the absolute value of x is large, the function is very close to the line y equals x plus 1 plus 0. This means that as x heads for positive or negative infinity, the graph of f gets closer and closer to the line whose equation is x plus 1. The line y equals x plus 1 is a slant asymptote of the graph. In general, if your function is written in the term of a quotient or a fraction, p and q have no common factors, and the degree of the numerator is 1 more than the degree of the denominator, you can find the slant asymptote by dividing q of x into p of x, and the division will take the form p of x over q of x is going to equal a line y equals mx plus b plus the remainder over q of x. The equation of the slant asymptote is obtained by dropping the term with the remainder. Remember, at very large values of x, that remainder will head for 0. Thus, the equation of the slant asymptote is the line y equals mx plus b. All right, let's try it out here. Find the slant asymptote of this rational function, x squared minus 4x minus 5 over x minus 3. Well, we're going to divide. X minus 3 is our denominator. We're going to divide that into the numerator, x squared minus 4x minus 5. And why do division that way when we can use a little synthetic? So I'm going to bring down my 3 and flip the sign. I'll bring down my leading coefficients. All powers of x are represented. Bring down my 1, multiply and add, and multiply and add. So what I get here now is y equals 1x minus 1 with the remainder of 8 over x minus 3. Well, as we plug in very, very large values of x, this remainder becomes 8 over infinity, or it heads for 0. So the slant asymptote is 1x minus 1. If we were going to graph this, here's our xy plane. And we can graph the line x minus 1. You know, we'd have our y-intercept at negative 1 and our slope of 1, up 1 over 1, up 1 over 1. So there is our slanted asymptote. We also have, back to the original function, x minus 3. What would zero out that denominator? Well, x equals positive 3. That would be a horizontal asymptote. And then our function is going to be some curves here approaching but never touching those asymptotes. All right, for checkpoint 7, graph that. Again, it will have the general shape of a parabola. And checkpoint 8, find that slant asymptote. Okay, step 1, symmetry is even, so it will have y-axis symmetry. 2, y-intercept. If I plug a 0 in for all x's, I will get 0 divided by 2, or 0. So that's my x-intercept, or excuse me, y-intercept. My x-intercept is I set the numerator equal to 0, x to the 4th equals 0 at x equals 0. So same for my x-intercept. Number 4, vertical asymptotes. Where does my denominator equal 0? X squared plus 2 will never equal 0, so there are none. How about horizontal asymptotes? My numerator is much more powerful, so there will be no horizontal asymptotes. And I can just graph a few other points. They would be in between the asymptotes and the x-intercepts, but since I have no asymptotes and only one x-intercepts, I know I have a y-axis symmetry. I can check positive and negative 1 just by checking positive 1. I'll wind up with 1 over 1 plus 2, or a third. So I'll have a couple points here and here. Let's jump to 3. If I plug in 3, I'll have 3 to the 4th, which is 81, over 3 squared is 9 plus 2, which is 11. That comes out to be a number pretty close to 8. So over 3 up 8, we would be up off the graph. So we look something like that. Close enough. For this one, it does say find the slant asymptote. And what the heck, let's graph it a little bit too. Why not? First, I can obviously see I'm going to have a vertical asymptote at x equals 2, because 2 minus 2 is 0. So here we would have our vertical asymptote. And for our slant asymptote, we would divide. Let's start right off with the synthetic. We're going to divide 2 into our leading coefficients of 2 minus 5 and 7. Bring down the 2, multiply and add, multiply and add. So our line is 2x minus 1, and then our remainder 5 would disappear at large values of x. So let's graph the line 2x minus 1. Well, minus 1 is our y-intercept, and our slope is up 2 over 1. So I'll plot a couple more points there, and we can connect the dots with a dotted line, giving us our slant asymptote. So let's try to find out here where our function exists, I guess. If I plug in a 0, f of 0 will give me my y-intercept. So all x is turned to 0, and I'm left with 7 over negative 2, or negative 3.5. So negative 3.5 would be down here, and that tells me I'm going to exist in this part of the graph. I will approach but not cross this asymptote, and also this one. Okay, let's see what's going on. Maybe I'll plug in positive 3. F of 3. So 3 squared is 9, times 2 is 18. 18 minus 15 is 3. 3 plus 7 is 10. That's my numerator. Denominator will be 3 minus 2 is 1. So over 3 up 10, and that'll put us up off the graph, so we're sort of up in here. Again, those asymptotes do continue to infinity. And we're going to look something like this. All right. And they didn't ask us to graph that. I was just having so much fun. I couldn't help myself. Homework, page 406 and 7, numbers 81 to 86.